More examples of curve sketching here with the increasing, decreasing, and concavity tables. So we're going to look at a function again that we know, 1 over x. We know that f primed of that is negative 1 over x squared, and f double primed is going to be 2 over x cubed. Okay. We know that f primed of x, any of them, do not exist at, or will never equal 0. Okay, and they don't exist at x equal to 0. You have a vertical asymptote at x equal to 0. And the numerator never equals 0, so these functions will never equal to 0. Okay, so the only critical number that I'm using here in the increasing decreasing table is 0, because the derivative never equals 0 anywhere, and you have a vertical asymptote there, so it could change from increasing to decreasing around there, as I showed you in a previous video for 1 over x squared. But this one doesn't. So if you take a look at the derivative, negative 1 over x squared, it is always going to be negative. It never changes sign, because x squared is always positive, and negative 1 divided by positive is always a negative. So f double primed is always negative, and this function is always going to be decreasing. Okay, so that's for that one. Now let's take a look at the concavity chart for this one. Okay, so in terms of concavity, we look at the second derivative. Well, it's done undefined. The function's undefined at 0, so that's a critical number for that one, because it could change concavity around a vertical asymptote. It could also change concavity around a point where the derivative is undefined too. The function might be defined, but the derivative might be undefined. We'll look at that in the next one example. So for this one, we're putting 0 as a critical number in this concavity chart. The second derivative is 2 over x cubed. When x is negative, x cubed is negative. So this factor, this piece here, is going to be negative. When x is positive, x cubed is positive, so this whole piece here is going to be positive. This is the second derivative, so we just transfer the signs down. And when the second derivative is negative, the function is concave down. And positive means concave up. So this is the concavity chart for 1 over x. It's a rational function. So with rational functions, we need to look at the end behavior to think about the asymptotes. Okay, so for the end behavior for this one, we're going to look at, or any of them, we're going to look at the limit as x goes to positive or negative infinity. Okay, so for this one, the limit as x goes to infinity of this, well, 1 over very large numbers tends to 0. So the limit equals 0. Same thing when it goes to negative infinity. Okay, so that means that y equals 0 is a horizontal asymptote. Because as x goes to infinity, the function tends towards 0. So y equals 0 is a horizontal asymptote. Okay, and then based on the information we've got, the increasing decreasing chart, we know that it's always decreasing. We have a horizontal asymptote, we have a vertical asymptote. The function is decreasing, and it's concave down here, so it has to be like this. It's decreasing here, and it's concave up, so it has to be like this. It never crosses the x-axis because we don't have any zeros for the function. Okay, so this is how this one works. Now, the next example is going to be an interesting one. This one right here, x to the 2/3. So f of x equals x to the 2/3. Taking its derivative, bring 2/3 down, subtract 1 from 2/3 gives you negative 1/3. It's going to be 2 over 3 times the cube root of x. The second derivative of that, taking this down in front and simplifying, you get negative 2 over 9 times the cube root of x to the 4th. Okay. In this one, f of x can equal 0. So when x equals 0, x to the 2/3 is 0. But f primed does not equal 0, because 2 divided by 0 is undefined, and 2 never equals 0. Okay, so you can't get f primed equal to 0. So we're putting that into this concavity or increasing decreasing table as a critical number, because it could change from increasing to decreasing around there. And when we look at it, it does. So f primed, when we look at this, the cube root of a negative number is negative. So this is negative when x is less than 0, and it's positive when x is greater than 0. So wherever the derivative could change signs, you have those numbers as critical numbers for the increasing decreasing table. So the function is decreasing before 0 and then increasing after. Okay, so now let's take a look at the concavity chart for this function. Well, the concavity, we're looking at the second derivative, okay, and again, it doesn't exist at 0, neither does the derivative, so we're putting that in here as a critical number for the concavity chart as well, because it could change concavity around where the derivative does not exist, or the second derivative. Okay. If we look at the second derivative here, we've got negative 2 over cube root of x to the 4th. Well, this is always going to be negative, because x to the 4th is always positive, cube root of a positive is always positive, so the negative out here determines the sign of this. So this is always going to be negative. And since it's always going to be negative, we're going to have concave down for both parts. So this function is always concave down. And it has no other zeros except for x equal to 0. Okay, so again, this function here equals 0 at x equal to 0. And then it's concave down. So the only possible graph for this, because it's decreasing here, increasing there, but concave down on both parts, that gives you this graph. And this point here, where it comes to that sharp point, and the concavity doesn't change on either side, that is called a cusp. Okay? It's also an absolute minimum for this function. The derivative doesn't equal 0 there, the derivative's undefined there. So you could have an absolute, or a minimum, absolute minimum, local minimum, whatever, where the derivative doesn't exist. The function would have to exist there, though. So this is an interesting case where the function exists at 0, but the derivative doesn't, and you get this thing called a cusp. Okay. Another interesting function is this one here. F of x equals x to the 1/3. Here's the derivatives, so you can check those. Here's the increasing decreasing table. Okay, the function exists at 0, but the derivative doesn't because of the denominator. So that is going to be a number in our increasing decreasing table and in the concavity chart or table. The signs of the derivative here are always positive because of this 2 number here, so that's basically squaring anything. That makes it positive, the whole thing's positive. So this function is always increasing. The concavity, well, x to the 5/3, these powers are odd, so they will change signs. So when x is negative here, x to the 5/3 is negative. When it's positive, it's positive. Because of the negative here, it's going to be the opposite signs. So f double primed is positive when x is less than 0, negative when x is greater than 0, which means concave up on this side, concave down here. This implies we have an inflection point because the function does exist at 0, but the derivative doesn't. Okay? The second derivative also doesn't. So we have an instance here where the second derivative does not equal 0 anywhere, but we do have an inflection point. So we have an inflection point at x equal to 0 because there is a change in concavity. So wherever there's a change in concavity and the function exists, that is an inflection point. Okay, so taking all this information, this is the graph we get. It's increasing here, increasing there. Concave up, concave down. the derivative doesn't exist here because the slope of the tangent is infinite. It's undefined, straight up and down. The tangent is vertical. Okay, so I call these a vertical inflection point. Okay, and so that's that one. And now I'm going to show you one that's more complex here.